So I'm Rob Lee. I want to spend some time talking about the software architecture. So Brian gave us a really good overview of the hardware architecture. And this gives us a really nice platform to build upon. It gives us a really nice platform to scale out the system in terms of adding more raw flash capacity, in terms of adding more compute power. But in order to tie it all together and present, a usable kind of unified file and object storage interface, we have to combine that with software, and we have to combine that with software that's based on an architecture that's going to support our scaling goals. If we kind of go back to the beginning and revisit the 3 dimensions of scale that we want to achieve in file and object storage that Brian laid out, we want to achieve scale in terms of capacity, right? Access to petabytes, tens of petabytes of data. We want to achieve scale in terms of concurrency, being able to handle thousands, tens of thousands of clients, as well as scale in terms of ever-increasing complexity in terms of access patterns. Right? From small metadata-intensive operations to serving large streaming I/Os, we want to be able to handle it all, and we want to be able to handle it all with a single unified architecture. And so, really, the insight here is that, in terms of scale, from a hardware perspective. As we add blades into the system, we're fundamentally adding raw capacity, and we're fundamentally adding raw compute in terms of cores. And from a software perspective, the key to actually unlocking that scale is providing a software architecture that is able to maximally utilize those cores as we add them to the system. Where scale-out typically falls short is that you reach a point of diminishing returns. You reach a point where adding more cores doesn't really help your problem, solve your problem, because of the tax you pay just managing those extra resources. And so we want to attack that head on. So if we look broadly at the space of challenges that scale-out storage faces, we see a lot of commonalities. If you kind of look at a really, really high level, right, what are, all scale-out solutions really at a high level look somewhat similar, right? You have compute and storage, and the physical form factor and makeup of this, varies quite a bit. You may have a dual controller architecture with a bunch of drives sitting behind it. You may have more of a blade type architecture like we have with a single compute unit with direct attached storage behind it. But at a high level, you really have 3 tiers, right? You have compute, you have storage, and then you have networking to kind of tie it all together and unify it. And so what this means is that in order to scale out, we have to find a way to create distribution and parallelism through each of these tiers. Right? We need to find a way to create distribution in terms of how we handle incoming connections at the networking tier. We have to find a way to distribute data across the system. Right? As we add more compute and storage into the system, we have to find a way to distribute that data across all of those new storage resources. And then most importantly and most challenging, we have to find a way to make use of the compute tier. Right? And as we scale it, we have to find a way to distribute that controller logic. And so what I want to do is kind of walk through each of these challenges, touch briefly on some of the common solutions we see in the market today, but really spend more time talking about how we've addressed some of these challenges in our software architecture.
Can I ask one question before you?
Yes.
That bit, Rob? When we look at the design there and you show 15 blades.
Yep.
What happens if I want 30 blades, 45 blades, or whatever? Is the system a logical connection of multiple chassis into one enormous
That's a really great question. And I think that really highlights the point that, at a high level, the physical form factor may be different, right? But at a logical level, we see that system as one large logical namespace. So.
Okay, because that wasn't really clear, I don't think, when we had the day when you presented to us at Accelerate, whether when you plug more than one of them, you would just extend one enormous logical system. Yep.
No, so we absolutely would extend one large logical system, and so whether there's 15 of these blades sitting here or 30, the physical form factor of the networking tier may change slightly, but from a software architecture point of view, we just see that as more scale-out compute units.
Right.
All right. So what I'd like to do, like I said, is just dive into each of these layers and touch briefly upon some of the common approaches that we see, but really spend more time talking about some of the design trade-offs and decisions that we've made that have influenced our implementation. So I want to start with talking about the networking tier and how do we go about addressing the problem of distributing the load associated with handling connections incoming from clients. And so one of the common patterns we see is really where, and I think Brian touched upon this a little bit, is where you have two independent networks. You have an external network and an internal network that you use for backplane traffic, control traffic, so on and so forth. And so a common approach in this architecture is really just to open up direct addressing to each of the compute blades in the system. By opening up direct addressing to the clients, what you're really doing is creating distribution of connections by essentially making that a client-driven problem, right? You ask you set up your clients in a way to load balance how they connect into the compute nodes that you add. And oftentimes you couple this with higher level load balancing techniques such as DNS-based load balancing, so on and so forth. But fundamentally, you're relying on the client here to create that distribution for you.
So there's not like a DNS load balancer in front of it or anything like that? Or
I'm sorry?
There's not like a DNS load balancing?
So in this architecture, commonly you will see a DNS load balancer. In our architecture, what we've done, as Brian kind of alluded to, is we've looked to collapse those historically two separate networks into a single physical network, right? By collapsing those into a single physical network implementation, what we can do is we can make use of the SDN software, essentially program the switch in a way to present a single network point of presence to the external world. On the external network, the entire system appears as essentially a single network endpoint, right? We should appear really no different to the client here as a host adapter, right? Except it's a host adapter with lots of pipes, lots of really big pipes going into it.
Can you describe how you're changing those switch ports? Are you doing something specific there to present that?
Yeah. So what we do is we program the switches to create a set of virtual IP addresses, essentially, or you can access the full bandwidth of the system through a single virtual IP address. For management reasons, a lot of customers prefer to have multiple, but that's really just a management kind of decision. From a speeds and feeds point of view, right, we can present a single virtual IP address, and it's link aggregated over all of the links that we can push up to the core switch. But behind the scenes, we program the switch in a way to load balance those connections across each of the blades. Right? And so the switches are really playing a
Are they all in a VPC?
So the blades are basically participating in an ECMP group.
ECMP, okay.
And so the switch is really playing a dual role for us, right? On one hand, to the external world, it's providing this veneer, this facade of a single network point of presence. And on the internal world, it's providing more kind of core switching capabilities for us. But what we get out of that is essentially transparent load balancing at the switching tier. And what we do with that is we load balance incoming connections across each of the blades. So as you add blades into the system, the switch is now automatically directing, through random distribution, directing new connections to those blades. And the way that we manage that is we set up the software on the blades to essentially do transparent kind of stateless connection forwarding, right? And this is conceptually no different than if you look at the FlashBlade product, for example. If we do I/O multipathing to both controllers, the passive controller is essentially doing stateless connection forwarding or I/O forwarding. And so in many ways, conceptually, we've just taken that model and pushed it out over each of the blades. All right. So I'm going to talk a little bit about how we achieve distribution of the data, right? So, as we add more blades to the system, we add more compute and storage resources. Our networking, our switch software gives us the ability to balance more connections to those new CPUs, but we still have to address the issue of how do we actually take advantage of the new storage resources and place data there. So one of the common approaches we see to solving this problem is what I call really namespace federation, right? And this is where you take parts of your logical namespace, whether it's file systems, volumes, directory subtrees, so on and so forth. You essentially map portions of those namespace to specific storage nodes. And once you've done that mapping, You then federate those storage nodes all together into a single namespace, and that gives you the ability to continue to scale this out. There are some benefits of this, right? It gives you the ability to access that data with very little coordination, right? Because you've mapped portions of your namespace down to a single storage node. You know exactly where to go for that data. You know exactly what compute node controls that data. But it does create other problems, right? It creates the problem of imbalance. Typically, what ends up happening here is you create islands of unused performance and storage capacity, right? It becomes very, very difficult to rebalance over time as your data sets shift or you want to expand the system. And you know, overall, it's just a very inefficient use of resources. So what we wanted to do was really just kind of step back a little bit. And at a high level, if we look at the control tier, right, all of the CPU resources across all the blades in the system, and we really just kind of squint our eyes a little bit and think of that as one single logical distributed controller. You know, we wanted to think about this problem very much the same way that a more traditional storage array architecture would look at it in terms of controller and drive shelf, right? And so if you take the distributed, you know, if you take the view that the CPU resources across all the blades form kind of this distributed controller tier, then the way that we view the storage really is very, you know, it's very similar to, at a high level to how a more traditional storage controller would view a drive shelf, right? Each of these are essentially independent failure units, independent you know, flash domains, independent units of NVRAM. And what we want to do is we want the system to be able to take advantage of each of these storage resources and form, for example, wide stripe, very efficient RAID encodings over all of the storage resources in the system. Now, in order to do that, that creates certainly a coordination problem in the control tier, right? We have to figure out if we're going to create RAID stripes and protection groups and so on and so forth across all of the blades, well, you know, how do we manage that? Who gets to manage that? And certainly that's a problem we have to solve, but I want to touch on that in a second. You know, from the point of view of data distribution, though, what we want to achieve is really the view that at the storage tier, this is conceptually not that different from how we would add drives to a drive shelf in a more traditional storage architecture. All right.
So data is wide striped across all the storage nodes in a FlashBlade cluster?
Yes. So, and you know, to a certain degree, right? So, you know, we really want to balance two trade-offs, right? We want to balance striping wide for encoding efficiency, but at some point, you know, you kind of get diminishing returns on that. And so as we expand beyond a single chassis, for example, we'll form kind of multiple sub-write groups, if you will. Really, you know, not that different from how FlashArray, for example, would stripe data across multiple controllers. Multiple drive shelves.
So is it a single chassis right now?
Right now in GA, it's a single chassis, and then very shortly after that, we're going to expand beyond a single chassis to multiple chassis. And to get to Chris's point from earlier, when we do that, we would still maintain a single, you know, global unified namespace.
You need to buy a full chassis, or you can start with only 3 blades?
That's a great question. So the smallest configuration starts at 7 blades, and we build out from there. The unit of expansion is a single blade at a time. And really, the reason why we start at 7 blades has to do with just efficiency, right? We want to provide N+2 redundancy. We want to provide the ability to lose 2 blades and still remain online and integral, which means that, you know, we have RAID encoding efficiencies and so on and so forth. And you know, you get too far below 7 and it just stops making sense. You really just have a triplicated system.
On your previous slide there, Rob, the one previous to that, you were talking about data distribution from a file perspective, but file isn't the only protocol you're going to support in this platform. So I'm guessing you're using that as an example, but
yep.
If you're supporting object or other types of data, I guess that sort of process wouldn't work because not everything's a file system that can be segmented up. You know, what happens when you've got a really big object? Would you distribute the object across many blades and then, you know, use that as a performance mechanism?
Correct. So I want to talk about how we solve that problem. You know, that definitely is a limitation of the federated approach, which is why we didn't really want to address the problem in that manner.
So I think we just make sure This is how many people do it.
Yes.
We choose not to do that.
Yeah, I agree. I realize.
I just want to make sure everyone on the internet ever follows along with that.
Yeah. No, fair.
So at a high level, we want to view our usage of the flash in the system as a system-wide concept. Now, how we break up individual objects or files across all of these resources is something I actually want to touch on in terms of how we manage to distribute and break up the control tier. All right, so this is really the meat of the problem, right? Connection distribution, data distribution, it's more or less fairly straightforward. The hard part of this problem is how do we break up this control tier? And just to level set, just to make sure we're kind of all on the same page, when I talk about breaking up the control tier, what I'm really talking about is, in this kind of three-layered system where you've got the networking tier handling external protocols, you've got the data at the bottom, there's all this stuff in the middle, right? There's all this logic that has to run somewhere in the system to do address space translation, namespace rules, and actually implement the file system, I/O scheduling, data placements, data layouts, coordinate background tasks like garbage collection, so on and so forth. And so really the problem is how do we create parallelism and distribution at this tier? So let's go back and look at some common approaches that we see, right? And again, this is what we see in the market. We want to kind of do something different. So if we go back to federation, right? Well, federation kind of sidesteps this problem, if you will, right? In the federated world, you have already mapped portions of your namespace, both data and control over those portions of the namespace, down to a specific storage node. And that applies a specific compute node. And so, you do get the benefit that there's not a whole lot of coordination here. But again, we're back into the world of islands of performance. You don't get the benefit if you have a workload that's especially concentrated on one portion of your logical namespace. What you really lose out on the benefit is all of the additional compute resources in the system. You don't get an opportunity to bring those compute resources to bear on your problem. The other approach that we see out there is what I like to call partial distribution. And with partial distribution, the insight here that people have had is, well, we want to unlock some of those additional compute resources in the system. So they want to create more global access to the shared metadata. They want to be able to allow these compute cores to address that shared metadata, but at some point you still are sharing the metadata across the entire system. And in order to mediate that access to the shared metadata, to mediate the kind of and create transactionality around updates and changing the system, you have to couple it with a locking system. You have to couple it with a lock manager. Now, you don't want a single lock manager because that's a point of bottleneck. So you create a distributed lock manager. But at the end of the day, you still have a system now where you can bring more compute power to bear by addressing metadata from any of these compute cores as you add them. But in order to mediate that access, you have to go through a locking tier. Now, this does simplify a little bit of the coordination because if you can achieve, if you can acquire that lock, you have, any of the compute cores can update and change that metadata, but it does come at a cost, and that cost is a lot of inter-node communication, very chatty messaging protocols typically, and what you really need is a very efficient lock manager or lock management implementation to achieve any kind of performance. So we want to do something different. We want to take that partial distribution, we want to go one step further, and we want to really achieve global distribution. What I mean by that is to really achieve parallelism and scale, the name of the game here is really just finding all of the efficiency that we can bring to bear in terms of metadata. Creating very efficient access paths to query your metadata, to update your metadata, removing all of the contention in that process, right? And that's really critical. The reason, the way that we achieve that is by creating deep parallelism and independence in how those compute cores can update and access the metadata. The way that we achieve that parallelism is by partitioning, right? We partition access to that metadata into independent portions that don't require lots of coordination overhead just to make any changes. So instead of sharing all the metadata, we take that globally addressable kind of body of metadata, and instead of allowing all the compute cores to make changes simultaneously and go through a locking tier, we try to break it up ahead of time and say, some portion of the compute world is allowed to make changes to this portion of the metadata. Some portion of the compute world is allowed to make changes to other portions of the metadata. And then we'll figure out how that all fits together in a bit. But at a high level, right, we want to create very efficient access to metadata. We want to reduce the contention and locking required to do that. We do that through deep partitioning. And the other thing that we need to do is we need to look at not only the online performance of the system, not only just the I/O paths, we need to consider what happens in the other case, right? The cases of failover, the cases of expansion, right? We need to have the property that as you expand the system, as you pull a blade or have a failure event, that we don't have the requirement to do lots of synchronous data movements to stay online, lots of synchronous data movements to restore backups or special purpose mirrors or so on and so forth.
I was just going to ask you that question. So if you're partitioning metadata onto each blade, and then you add twice as many blades, does that mean you then have to split the partitions and distribute it, and vice versa? If you lose 2 blades, there's some sort of collapsing of that metadata have to come in order for others to suddenly say that, well, I'll have to take more of that partitioning.
So that's a great question, and that has a lot to do with how we manage those partitions and how we break the namespace into those partitions.
But you'll have a picture of that.
And yeah, I'm going to address that in a few slides and hopefully answer that question.
Mm-hmm.
So what does this look like at a super high level view? So at a super high level, imagine that we could take, I think the best view of this is imagine that we took that logical controller tier and we split that problem into lots of different independent pieces, right? And instead of running one control process, we run lots of them, right? They all operate on different parts of the namespace. They all operate on different parts of the storage. And they operate independently, right? That's really the key here, is that they're independent and they can run in parallel. Now, imagine, leave aside for a second how we managed to break the world up this way, right? Because I will get to that. But just imagine that we do. So now that we've created these independent partitions, what we'd like to do is be able to run, well, many of these partitions on each blade. And part of the reason for that is, if you do have a change in topology, we want to be able to pick these partitions up, migrate them to other physical blades, and run them there.
I guess, sorry to interrupt, Rob, but that means that you could run a completely an asymmetric configuration. You could have blades that are bigger than others, because some blades could run more processes than others if they've
That's a good idea. Yes, exactly. And so, at some level, you can almost think of these. You can almost think of this concept as splitting and somewhat virtualizing. Right? We want to virtualize the work involved in managing a portion of the namespace. We want to make it easily migratable. And again, getting back to kind of that instant performance goal, our ability to pick up a partition and move it somewhere else very quickly without doing synchronous data movement is really key to kind of instant online expansion and failover.
And performance instantly.
All right. So, just to kind of drill down a little bit, once we've split the world into each of the, into these independent partitions that can operate in parallel, we get to split the responsibilities of that larger controller tier. We get to split the responsibilities of managing portion of the namespace. We get to split out the responsibilities of creating data layouts, managing data protection, doing background maintenance, GC tasks, FTL tasks, so on and so forth. The beauty is now these can all run in parallel, right? And that parallelism is really key to achieving scale. This is what gives us the confidence that as we add more blades in the system, as we add more CPU and DRAM, we can take advantage of that CPU and DRAM because each of these partitions is more or less independent. So, well, how is it that we can actually pick up these partitions, move them without moving data? And so I think this is, one of the insights that we had early on was that what we really want to do is create a view of the world within each of these partitions, right? Going back to the mental analogy that, each of these partitions is essentially a slice of the controller. Well, we want each of these partitions to see the storage layer very similar to how a controller in a more standard, storage array architecture would see the world, which is essentially an array of drives, an array of storage resources. So from the point of view of each of these partitions, the partition sees storage resources, flash and NVRAM, on each of the blades. It manages the flash and NVRAM, or a portion of it, on each of the blades. Conversely, each of the storage units on each of the blades provides a portion of the storage. It kind of at a high level, you can kind of think of it as a bit of multi-tenancy, a bit of isolation. So within each of the storage units, it's providing.
Each of those blocks of CPU DRAM are really multiple blades, right?
So in this view, in this architectural view, really this is one blade, right? So each blade is providing a CPU and DRAM on the.
How do you minimize a single point of failure when that blade goes down and its metadata and its associated slice of all the storage goes away?
That's a really good question. So we look at failure as really kind of in two tiers, right? There's the control tier and then there's the storage tier. From the point of view of storage, when that blade goes away, it's really no different than pulling a drive from a more traditional storage array architecture, right? You pull a drive, you've already striped the data or replicated it across all of the other storage resources in the system, right? So from the storage perspective, a failure is really no different than that. From the control or compute perspective, right? Remember, we have the property that we can pick up each of these partitions and we can migrate them to any of the other blades. And because these partitions, there's no data, there's no state associated with this partition running on this particular blade. We can pick up this partition and migrate it to other blades without moving data around, because all of the state associated with this partition is striped across the entire storage tier. And no matter what physical, compute core, physical blade this partition happens to be running on at any given point in time, it derives its state through that global storage tier.
That's really neat. So you're like running containers of processes there to actually manage each of the bits of the workload.
Exactly.
Kind of like microservices.
Yeah, kind of like microservices, yeah.
And I think that's a really good analogy. All right, so just to recap, these partitions, or internally, we refer to them as authorities. And I think we use that term because the realization is that these partitions are not just static. They're not just about data, right? They're about control, right? These are really active partitions. And so internally, we refer to these as authorities. And so each authority is shared nothing in the sense that they manage an independent, non-overlapping portion of the namespace, a portion of the metadata. They're independent, so that creates parallelism. They run, without a ton of coordination between them, and they're relocatable, right? We can pick them up and move them without doing a ton of synchronous data movement because there's no state associating that partition or that, quote unquote container to the particular blade it happens to be running on. And so again, just kind of reinforcing it, my favorite mental model is that each one of these really conceptually is very similar to a mini flash array controller. We just containerize it, make a whole bunch of them, and then we have to figure out, well, how do we break the world into these things and how do we move them around?
So in a normal controller, metadata like that would either be on the storage or in DRAM, right? And in your situation, you're using not the server DRAM per se, but using NVRAM and flash to maintain that state of the namespace.
And we will cache.
We'll cache
the DRAM, but that's not the state. That's the acceleration.
Exactly. The store of record, the gold standard of state, is.
It's a write-through cache and it's a read cache kind of thing for metadata.
All right. So.
And I think you're hinting at something that's very, very important. I know you'll talk about it later. If you want to make the system run fast, you now need to make sure that the way you preserve state to that persistent layer has to be extremely fast and extremely parallel. And thus, we designed hardware that is specifically optimized around that, which is what Brian talked about.
It's
So
one
now we're starting
access
to
NVRAM that's associated with the same server, but now you're having actually access NVRAM that's associated across multiple blades.
across all of the servers.
Yeah, and so it's, yeah.
Well, so remember, if we look at the storage tier as really providing the persistent state of the system, right? The persistent state associated with a particular partition. At runtime, that doesn't prevent the partition, right, as it's running from kind of caching that state in core on.
No, I understand that.
So really, it's a matter of how much state do you have to read when you move a partition, when you kind of rehydrate it from the world. And so we've done quite a bit of work. In terms of, I think Brian alluded to earlier, we borrowed a lot of concepts from Purity. We did quite a bit of work here to minimize the amount of data that we have to read back on kind of partition movement or partition start to make that process very, very quick. All right, so So I presented this really high-level view of the world. It all sounds really well and good. If we can break the world up into these nice little partitions, we get all kinds of goodness from it. Okay, so how do we actually go about doing that? How do we go about breaking the world up into this nice little view? And so here, we kind of borrowed one common concept from computer science, which is if you have a problem, add a layer of indirection. Here we're going to borrow the other most used concept in computer science, which is if you have a problem, see if you can solve it with a hash table. Right? And so what we want to do at a logical level is essentially take all of the globally addressed content in the system, whether these are files, object IDs, so on and so forth, data, portions of, the data in portions of files or objects. We want to find a way to take all of that globally addressed content and essentially hash it down to a number, right? Now we have to do this intelligently because we want to provide balance and we want to provide essentially randomness to, protect us against particular types of workload imbalances. But at a high level, what we want to do is take all of the global content in the system and hash it down to a number. And once we hash it down to a number, we can break up that number range into an arbitrary number of these partitions. And now we've kind of flattened the world and split it up. Right? So we do this with object IDs, inodes, for example. We do this within for portions of the file. Right? So for example, to Chris's question earlier, what do you do with a very large file? Well, we don't want all of the access to that file colliding on a single partition or a single blade. So we take a large file, and we hash both the file identifier and a portion, kind of the section of that file that we're working on, and we'll hash those to different partitions. So if you're working on a terabyte-sized file or a very small file, we want to create balance across the system. For any given I/O, you're not going to pay an additional cost or concentration for working on a large file versus a small file.
So Rob, just really stupid question, I guess, not understanding how you do it type question. But if you split up the address space range, or how you want it, the namespace, however you want to describe it, and use some sort of hashing algorithm to do that, does that mean you always have to have it going into a fixed number of target units? Because otherwise, if you change the number of units, the algorithm now doesn't work because some of them are now in a hashed.
So that's a really good question, and this really goes to expansion, right? This goes to, well, what's the right number of buckets, right? And there's a balance there, right? You want enough buckets so that you have balance, so you can fail a blade and you have enough to move around and create balance. But you don't want so many buckets that you pay this enormous overhead of just tracking where all the buckets are.
And I guess if you've fixed a set number of buckets, that limits the number of blades.
Exactly.
You can't have more blades than buckets.
Exactly. And traditionally, the problem, the real hard problem with changing the number of buckets is, well, how do you do that without globally rehashing the world?
All the data, yeah.
And so this kind of gets into the details of how we represent the metadata internally. Natively, we represent all the metadata in a native key value store, and this is the code that Brian alluded to that we pretty much ripped off from Purity. We have a very highly optimized in terms of access, query patterns, and storage, and so on and so forth, key value store that Purity uses that we've borrowed. And really the way that we store the metadata and the way that we've mapped the address space into these ranges allows us the ability to split these ranges, right? So rather than rehashing the world, what we say is it's kind of like if you go back to high school biology, right? You have cell division through meiosis, or we use that term internally, right? As we grow the system, each of these partitions will undergo a meiosis or meiotic process and essentially split, right? And so what you can do is achieve that without creating a global rehashing or data movement. You can achieve that by essentially doing tiering of faulting, essentially. And you can localize and contain that cost to make it constant.
So if you split a file into multiple chunks, how do you define the size of the chunk?
So that's a good question. So what we did was we looked at a variety of workloads, and this is partially experimentation. What we want to do is we want to balance. We want to balance the two trade-offs of creating efficient access to the majority of small files, but not create overwhelming concentration for very large files. And so internally, through all the experiments that we've run, we found that 16 megabytes is a pretty good trade-off point. But that's something that we'll continue to look at internally.
Okay. Yeah. Thanks.
So to give everyone a good idea, so when you get a request for a read, for instance, you have a file ID, and you have an offset. Those two combines creates a hash, tells us predictably exactly where it exists.
Yep.
So it's very, very fast to look up.
So that's a really good segue. Let's just walk through how all this fits together in terms of the data path, right? What happens when a write comes into the system? So when a write RPC comes in, when it's received by the system, it comes over a connection. That connection's been load balanced by the switch to one of the blades in the system, essentially a very thin layer of the software stack running on that blade that's providing that protocol tier, that protocol layer. And so at that layer, when we receive the RPC, the first thing we do is a very quick decode of that RPC, a partial decode, just enough to see, we don't have to look at all the data here. We look just enough to see what file or inode that write is referring to and what portion of the file it's referring to. And we take those two pieces of information and we essentially hash or map those to a partition in the system, right? These two pieces of information uniquely identify which partition should handle this write. Everybody agrees on that. It's just a known global function. And once we've identified which partition or authority needs to handle that write, we'll forward the RPC over to that authority. And from this point on, that authority can independently make, kind of retire that operation, write that, take that write, encode it, so on and so forth, and commit it to persistent store. And so when that authority receives the RPC, it will compress the data, right? We'll stage that, we'll kind of update our in-core write buffer, our kind of coalescing buffer, and we'll stage that NVRAM update, right? We'll push that out to at least three different NVRAM devices to make it persistent and redundant. And at this point, once we've positively acknowledged that we've written to three different NVRAM devices, we can consider this write integral, right? We know that we can fail any two blades and that write will have happened. And so at this point, we can reply back to the client because that write is integral in three different NVRAM devices. So we send the reply back to the client. And if we stopped here, the system would run really fast for about 5 seconds, and then NVRAM would fill up. So in the background, what we need is a process to evacuate or flush that NVRAM out to longer-term storage, more efficiently encoded storage. And so here's where each of the partitions, again, running independently in parallel, will periodically, as the write buffers fill up, do an intelligent kind of write, data layout and coalescing of in-flight writes, and push those out to the flash layer in a much more efficiently encoded wide RAID stripe. Cool. All right. So at a high level, what this really leaves us with is kind of two logical tiers of scale-out that we manage, right? We look at the system really as a logical tier where, how we break the world up into these partitions, how we move the partitions around, and a physical tier, right? How we make use of the additional flash resources, the additional NVRAM resources as we expand the system. And so, again, the logical tier, this is really just all about how we manage these authorities. At a physical tier, it's about how we manage all of the flash and NVRAM as we expand. And so let's just walk through.
Does every blade have access to every amount of NVRAM in the chassis directly? I mean, can it do a memory write, or is this like RDMA solution, or? So
it's a good point. So logically speaking, every partition, every authority running on any blade has access to a portion of the NVRAM on any of the other blades. That's at a logical layer, right? At a actual physical communication layer, there's a very thin layer of software, just like we had a very thin protocol layer mediating access to outbound NFS. There's a very thin software layer here that just provides kind of point of presence access to each of the storage units. So any of the partitions can address any of the NVRAM, and it does, there is a small kind of layer here to advertise that access. But the important point here is all the data transfer is happening it's really being orchestrated by the storage unit. All the real data transfer is being driven by the FPGA. So we do a lot of work in software to really reduce the cost of that communication. We do zero copy. We do user space networking, so that communication does go over Ethernet, but we do everything in user space, so we bypass the kernel. We do essentially zero copy down to the storage unit because we can basically just program the FPGA to do all the data transfer against that raw kind of mapped memory address. So it's not RDMA in the kind of Rocky or InfiniBand sense, but we do everything that we can to reduce to cut the costs out of every layer.
And we're using some specialized networking techniques because we control the network domain very closely ourselves.
So let's walk through an example of, kind of use this term, instant performance, right? Let's walk through an example of what happens when you add a blade. So we've got a system, it's in equilibrium. Use a diagram, there's more than 3 blades here, so imagine there's more. So we've got a system in equilibrium, we've got an empty slot we'd like to expand into. So, the first thing that I want to tackle is, well, what's the view of the world from the storage tier, right? As we insert a blade into this slot, how does the system view the storage across the entire chassis or the entire system? So, as you add a blade into this empty slot, that storage tier immediately expands, right? Each of the authorities essentially independently sees that new storage unit and has the ability to start placing new data there, right? It has the ability to start utilizing that new NVRAM resource. It has the ability to start forming RAID stripes that include the new flash, right?
And that's before actually any
exactly.
Before
any of the authority movements
taking place.
Exactly. And so again, from this layer's point of view, conceptually it's not that different from expanding the drive shelf, right? Just adding another drive into the system, right? Now independently, if we look at the compute tier, right, in addition to adding this raw storage, we've also added a bunch of compute cores and DRAM. And we'd really like to be able to take advantage of that. And so at the compute tier, what happens now is we form a global consensus that, hey, there's these new unused compute resources, and we'd like to migrate some of these authorities over to this empty blade, right? And again, I want to highlight that migration is because these authorities, these partitions, or these kind of containers are essentially stateless, right? They're stateless in place. That migration is very, very quick, right? These authorities derive all of their state from this shared storage layer. All right, so we could stop there. And if we stop there, we'd have a really, really high performance object system, right? But it turns out that in a richer file system like, for example, NFS, you have another problem to solve, which is the world doesn't always cleanly stay within each of these partitions, right? There are some operations in the file system that do require transactionality that expand beyond the boundaries of a single partition. And a really good example of that is what happens when you rename a file from one directory to another, right? If those 2 directories are mapped to 2 different partitions, right, you need some level of transactionality to ensure that, well, as you do that rename, you don't accidentally end up with 2 copies of that file or accidentally end up dropping it from both sides, right? You have to actually create some amount of coordination there. And this is really the elephant in the room, right? This is the hard problem that we wanted to address. And so if we look at kind of traditional approaches to addressing this problem, there's many different approaches. At a high level, I think they all boil down to 2 large categories, right? One is what I refer to as kind of the global lock, right? Now nobody's going to call it a global lock, but at some layer, if you peel back kind of all the details, you'll find a global lock somewhere that serializes access. You may find a tree of locks, right? You may find a hierarchy, but at some point there's serialization that gives you that kind of that consistent transactional view of the world. What we'd like to do though is remove that point of serialization, because any serialization in the system goes against parallelism, and that creates a bottleneck. The other approach that we see out there is really a pessimistic model for coordinating distributed transactions. And I think the best example of this is the two-phase commit protocol, right? This is something that has come out of the database world. It's very popular. It simplifies kind of the implementation and atomicity, but it comes at a cost, and that cost is essentially optimizing for the uncommon case, right? You pay a lot of coordination traffic, of chatter, of messaging in the common case just to handle the uncommon case of resolving a failure. And so we'd like to flip this on its head, right? Anytime that you're paying a cost in the common case to handle the uncommon case, it's a source of inefficiency. So we'd like to flip it on its head and try to find a way to optimize for the common case. So if we take a look at how a typical two-phase commit protocol would work, kind of the first phase, you have the the initiator of the transaction or the coordinator communicates out to all of the participants, right? So in this case, if we take the example of a file rename, for example, your participants may be the authority that owns the source directory, the authority that owns the target directory. Maybe you're renaming over an existing file, so you have to remove that, right? So you've got a bunch of participants. The initiator communicates out to all of them and says, hey, I'm about to start this rename operation. You need to create a link in the target directory. You need to remove a link in the source directory, so on and so forth. Now, each of the participants will commit that kind of conditional change to persistent store, right? Saying, if this transaction commits, then this is the effect that should happen. And then the result is communicated back, and then only after a positive acknowledgement from all of the participants do we then get to record the final commit record, right? It's kind of, and that's the two-phase, that's the second phase. So, you can count up all the arrows on the screen. There's a lot of communication, right? There's a lot of trips to persistent store. We'd like to improve this, right? And the way that we've improved this is by flipping on its head and defining more of an optimistic protocol, right? We want to optimize for the common case. And so the way that we do this is we start the process very much in the same manner. We still start off by communicating the intent to make the change, right? The intent to unlink a file from the source directory, the intent to link a file into the target directory. But the difference here is that instead of these partitions independently recording that kind of conditional or predicated change, they communicate back to the initiator saying, okay, here is the record, here is the metadata update I would like you to make on my behalf. And so what that allows us to do is to have the transaction initiator essentially coalesce or combine all of those independent metadata updates into a single commit record, right? And what allows us to do that is deep integration with the storage unit, right? We've pushed a very expressive transaction engine into the storage unit, into the way that we've implemented our interface to global NVRAM that allows us to express that level of transactionality over a very, very large NVRAM address space, right? We're talking about gigabytes per blade. It's a very large address space, but we need to, in order to optimize the high-level protocol in this manner, we need the ability to express transactionality over that large kind of randomly addressable address space. And the way that we do that is by deeply integrating with that NVRAM interface that we've co-designed in the FPGA. And so what that allows us to do is remove a bunch of intermediate communication, which, by the way, is all serialized, right? In the two-phase commit protocol, you can't actually respond back to the client until all of this stuff has happened and you've written the final commit record. So all of that latency is serialized. What we've been able to do is collapse all of that and push it essentially into hardware. Now, we still have to solve the failure case, right? I said we want to optimize for the common case, and if we have to pay an additional cost in the failure case, we'll do that. And the way that we do that is, well, each of the partitions, each of the authorities has global access to all of the NVRAM in the system, right? So there's always the possibility that the transaction coordinator failed or was pulled before that transaction commits. Well, these participants can directly go to the storage layer. They can directly go to that NVRAM layer and just look and see, did my change, the change that I told the coordinator to record for me, did that change actually make it, right? And we can tell by going essentially to that storage layer that's giving us the store of record, that gold standard, did the change actually happen? And we can resolve any kind of conflicts or do any kind of reconciliation by just going directly to that global storage layer. So, at a high level, if I boil down kind of our approach to handling the distributed coordination problem, really it's two-phase, right? First, we aim to do less, right? We want to create a protocol that just does less work, has less messages back and forth, less trips to persistent storage, and whatever's left that has to be done, well, we want to find a way to accelerate that. And the way that we've done that is by co-designing hardware to really push a lot of the typical challenges in terms of creating transactionality and transactional access to large amounts of randomly accessible storage, push that into hardware, because hardware is really, really good at that. Now, we didn't start out by building this, right? Brian mentioned that, from a hardware platform perspective, we staged our development, right? We built the alpha system out of, kind of 1U chassis to give the software team something to develop against. Well, we didn't start by building all of this either, right? We started really by building a two-phase commit protocol. Later on, as development proceeded, as we had more cycles to kind of push a lot of this transactionality into the NVRAM layer, and we had more cycles to kind of think through the distributed transaction protocol, then we've implemented this, right? And so that gives us kind of a good data point of, well, what do you get by going down this path? What we found was that we were able to reduce end-to-end latencies by about 3x by doing this, right? We were able to reduce back-end communication, trips to NVRAM by about 6x. And this has a very direct implication on the bandwidth that you can push through the system, right? And so, at a high level, one of the questions Par led off with was, why in the world did you build your own hardware, right? And that conversation has been kind of brewing. It's been, been getting lots of chatter around that. Most of that conversation has really been focused around the path to NAND, right? Most of that conversation has been around, custom NAND controllers or SSDs. But in many ways, I think the real kind of, the real star of the hardware story here is that integrated NVRAM, because that's really, really critical to enabling the software architecture to achieve this deep parallelism and distribution without paying inordinate tax for that coordination. So if I leave you with three takeaways from the software side, point number one is that we want to achieve scalability by creating parallelism at all layers, right? We really look at the scalability problem as a holistic problem. We have to find ways to create distribution at each of those layers, the networking, the compute, and the storage. The way that we create that parallelism is through deep partitioning, creating independent parallelizable units of work and creating distribution among those partitions. Now, deep distribution comes at its hacks, right? There's a cost to doing that coordination. And so the third point is, well, we want to do everything in our power, software and hardware, to minimize that cost. So what does that get us? So this is the results of just some internal IO-intensive benchmarking. And what we're really looking to see here is, can we create linear scale, right? As we add blades to the system, do we get a proportionate increase in performance in the system, right? Par used an interesting unit earlier, which was gigabytes per second per blade. And that's really how we want to think of the system. Right? We want to think of the system as you add a blade, you get proportionately more performance. And our internal testing has definitely shown this. On the read side, we're getting just north of about a gigabyte a second a blade. Gigabyte a blade a second, however you want to look at it.
And if I may, it's not benchmarking. This is us just running sequential IOs from a bunch of containers on a bunch of clients over 10 gig Ethernet on one single NFS share. Nothing special.
And so what we get, results have shown very, very linear increase in performance as we scale the system out. And again, this really boils down to creating parallelism at every layer, from the flash access, the lowest levels of access to NAND, all the way up to the highest levels of how we split the control logic. But this is our internal testing, right? It's not benchmarking, but it's still internal testing. Here at Pure, we focus on real-world results, right? So we want to look at, I want to shift our attention to some results that have come from an early access customer. Right? And so this customer, it's a car manufacturer, but it's really a software development house, right? There's a ton of software that goes into cars these days. A lot of it's firmware, a lot of it's bespoke software, there's third-party tool chains. One of the big pain points that they have today is just coping with the aggregate load on the storage from doing all that continuous integration and builds and testing, right? You have a bunch of engineers making changes, it takes a whole bunch of compute to do the builds, and then when those builds complete, there's just a whole bunch of data that has to be written to storage. To parallelize those builds, each step of the build writes the storage, it reads back the outputs from previous steps, right? So they've created these deep build pipelines to shorten their time to testing a change, but they've put in a tremendous load on the storage layer to kind of coordinate that. And so when we started engaging with this customer, they had a leading vendor deployed. And one of the problems that they're trying to address is, well, how can we push more concurrent builds into the system, right? At some point, when they have more than about 20 concurrent builds, well, the process takes over an hour and it just stops becoming interesting, right? Engineers, you get past a certain point and engineers get up, they go for coffee, they go for lunch, and you just lose a ton of productivity that way. When we started talking to them, they were actually saying that because as they scale beyond about 20 concurrent builds, the storage just kind of hits that point of locking up, that they have engineers that have essentially built processes in place to throttle the number of builds that their server farm can throw at the storage. That's not their core competency, right? They should be building cars.
And just to be clear, it's not too dissimilar from any other software. Very similar to the way we build.
Yep. And so we engaged with them and we deployed our smallest system, a 7-blade system, 7-blade FlashBlade system, and immediately dropped those build times from the 1 hour, kind of 60-minute range down to less than 10 minutes.
Was the leading vendor an all-flash system?
They tried both all flash and without, but because of metadata is the problem, and because there's so much data,
It doesn't matter.
It doesn't matter. I mean, this is kind of the secret sauce. When you talk bandwidth, the backend matters a lot. When you talk coordination across lots and lots of clients, coordination matters a lot.
So we really achieved two important things here, right? One is we materially moved the line of, well, how long do these builds take, right? We can make engineers much, much more productive by just shortening this latency. The other really important point that we've done, though, is we've now created the ability for them to scale to more and more concurrent builds, right? They've been able to triple the number of builds, even on our smallest system, and keep it within kind of manageable time window expectations. This gives them more testing cycles, and at the end of the day, helps them get their product, a car, to market a lot faster, right? This is real-world value here. Now, we didn't stop there, all right? We then took their system and we upgraded it to a 15-blade system. And what we saw was, a further 33% reduction, about a third, in the build time as we go to 15 blades. But more importantly, we've reached the point here that their client tier, they just need to add more clients, right? We've scaled to the point where they can throw more builds at it, but they've run out of clients and they've run out of networking on the client tier, right? And so really at a high level, this is what we want to do. We want to take storage and find places where it's currently the bottleneck and people are doing unnatural things to kind of cope with that, to work around that. And we want to make it not the bottleneck, right? We want to move the bottleneck somewhere else.
But you're doing that for a very specific workload that you can build concurrency into the workload, and therefore you can use the scale out and the parallelism of your platform to do that. This isn't designed for a month.
Because you've got multiple development organizations or teams that are spinning up these builds to do a test or something like that.
Or even one build, right? So if they did one build end to end, it would take, I think it was like 6 or 7 hours. So they've taken that build and they've parallelized it into 30-minute chunks or 1-hour chunks.
But what I'm meaning is that this is particularly targeted at those bottleneck issues that can be fixed by having lots of concurrent tasks and splitting the workload down and having it more distributed, rather than it being the flash array product, which is targeting a very different issue.
And I think that, and getting back, kind of coming back to Par's original setup slide, I think that that's really typical of what we see in this portion of the market, right? We see really the need to connect more and more compute clients to the storage, right? We don't see, frankly, a whole lot of workloads where you have a single stream, a single client that's, writing a massive pipe, right?
Yeah.
What we see is just this aggregate demand to connect more compute power to the storage, but the storage hasn't kept up, right? It hasn't been able to serve that.
But do you think that's part of the scenario we've got to with Moore's Law, where we now can't really scale up anymore? We can't make the process smaller, and what we're doing is we're putting more cores out there, we're putting more processors out there, and inherently computing is going to go to a more scale-out model naturally, because we just can't push Moore's Law any further.
So I think you're seeing a lot of that, right? I think that there's only so much you can scale up. There's only so much you can make things faster just by making the primitives faster. At some point you have to bite the bullet and you have to find ways to create parallelism, right? I look at this very much in the same way as if you go back to like I don't know, the late 90s, early 2000s, there was this, in the chip world, there was this race to make, chips faster, right? The clock frequency race. At some point that kind of topped out, and, hardware manufacturers started building, SMP boxes, multi-socket, right? Multi-core came very quickly. And at first that was kind of, it's like, but at first you could deploy, software on top of it, and you wouldn't really get all the benefits. To really kind of get the benefits of that, you had to re-architect your software. You had to build software with parallelism in mind. And in some sense, I see a lot of, kind of analogous trends in storage.
But I think, if I'm taking a step back, yeah, that is the trend. The modern software deployments that we're seeing are becoming increasingly distributed versus monolithic. All right. The database world is kind of successful with that, but if you look at the analytics world, they already moved past that.
Yeah, that's it.
Cool.
And that, if you're going to make a bet for the future, that's a pretty good bet to make.
Okay.
So I think I closed up a little bit of the time gap. We're pretty much at the limit of our time. If there are any last questions for any of us, we can take those, but I think we just have Steven's coming over, so maybe we don't have time.
One thing about the NFS version that you're using.
Yeah.
Is there a reason why you didn't go to 4 for security purposes?
Let me tackle that. So we picked 3 over 4 or any other protocol you wish, strictly based on amount of deployments out there. Strictly based on that. And there was no technical reason. It was just that much workload out there that ran on 3 and that really didn't need the benefit of 4. And so strictly on
a
starting point.
Layer of overhead to it, right? But on the flip side, all your intercommunication is all private. You're considering that?
It's just work.
Okay.
It's just work.
I don't think it's just software.
It's just software. We try very hard to make sure that we don't have NFS-ism into the system, so that over time we can change and add more and more protocols to it without normalizing everything to a file interface underneath it, right? Like we're not going to put we want to avoid that, and that's what I'm saying. This was picked strictly based on early adopters and entry into market. It was not picked based on belief that was a better protocol or easier to implement.
Okay. All right. Anybody else? No, I was just kidding. No, go ahead.
The blade communication are made only in the backplane.
Correct. And we're using, as I said, we use 10 gig Ethernet as signaling. And of course, internal to our system between the blades, the protocol is not TCP. It's a protocol we designed that's optimized around the patterns that we have, and that bypasses sort of the kernel inside of these blades as much as possible, because you don't want to spend time in there. And we know quite a bit about it. And like you hear a lot of us talk like it's an SDN and we have this sort of low latency fabric. That is true. We've done quite a bit on the protocol side and communication side to optimize for the communication.